Welcome everyone to this video by Learn Civil Engineering, where we will be introducing the different types of loads that can be applied to structures, and then the different types of supports used for connecting members of structures to foundations. Throughout the video, we will see some real-life examples of each and how we can denote them for easy use within analysis. As a civil engineer, regardless of the discipline, the structure being designed must be able to withstand any loads that will likely be applied to it. For example, a building must be able to withstand the load from its occupants and furniture, to name a couple, and then the pavement forming a road must be able to withstand the load from all vehicles travelling along it. When considering buildings specifically, the loads that could be applied include forces caused by the weight of the structure itself, the occupants, furniture and other content, walls, wind, snow, and earthquakes. In this section, we will take a look at the different types of loads that can result from these forces, and how we can denote them clearly for others to understand. In the last two videos, we saw that forces applied to a single point, also known as concentrated loads, can be represented by vectors, where the arrow represents the force's point of application and direction, and the length corresponds to the magnitude. And we have also seen that moments can be represented by a curved vector. An example of a concentrated load is a person standing on a roof. Although the person's feet still have an area in contact with the roof, the area of contact is negligible compared to the area of the roof, and therefore we can say that the feet have negligible dimensions but significant mass, and just for this example, let's say the person weighs 0.7 kilonewtons. The result is a concentrated load being applied to the roof where the person is standing. It is possible to see forces applied to single points in structural analysis. However, it is uncommon as most loads are applied over a length or an area. Taking the example we just looked at, whilst standing still, the person is considered as a concentrated load, but in reality, the person will not be standing still forever. Therefore, the person would be considered as a dynamic load. A dynamic load is defined as a load that changes in time quickly compared to how the structure can react to it. From our list at the start, this can include loads due to occupants, wind, snow, and earthquakes, but we will cover dynamic loads in more detail in a future video. A distributed static load can be represented by a set of smaller arrows, indicating the magnitude of the load with respect to the length that is being considered. A uniform load is represented by a set of arrows which stay constant with respect to the length, as the magnitude of the load is uniform along the length. Only a single number is required to represent a uniform load. For example, a wall of length 10 meters applies a uniform load of 3 kilonewtons per meter to the ground. Using this information, we know that over a length of 1 meter, a total of 3 kilonewtons will be applied to the ground evenly, and we can therefore work out that the 10 meter length of wall has a total weight of 30 kilonewtons. Secondly, a linear load is represented by a set of arrows that increase or decrease at a constant rate with respect to the length. To denote a linear load, we require the load at 2 points along the length. For example, the load applied by a homogeneous liquid to the wall of a dam increases linearly with depth. With the load being known at just 1 point, it is impossible to work out the linear distribution of the load. However, knowing the load at a second point allows us to calculate the linear distribution. Here, for example, the depth of the water is 10 meters, the load applied to the dam at the surface is 0 kilonewtons per meter, and the load applied to the dam at the base is 10 kilonewtons per meter. Therefore, we can see that the load increases by 1 kilonewton per meter for every meter deeper we go. And so, at a depth of 5 meters, we can say that the load is equal to 5 kilonewtons per meter. Note that these numbers used may not necessarily be realistic, however, they do get the point across easily. Finally, a parabolic load is represented by a set of arrows that increase or decrease with respect to the length following a parabolic line. Parabolic loads are less common than uniform and linear loads, but are used in analysing wind pressures applied to buildings. Having now introduced the different types of loads we will encounter in structural engineering, we will now take a look at the types of supports. With a structure, the loads applied to various members are carried to the ground through foundations. And, for ease of analysis, foundations are represented as a function of the forces or moments they transmit, which are called the fundamental supports. Foundations can be categorized under the following fundamental supports: fixed, which transmits forces in any direction and moments in any direction; pin or hinge, which transmits forces in any direction but not moments; and finally, roller, which transmits forces in only one direction. A fixed support allows no displacements and no rotations of the member connected to it. A pin or hinge support allows only rotations of the member connected to it, and a roller allows rotations and displacements parallel to the support. A real-life example of a fixed support is this column connected to the foundations, as the displacement and rotation at the end of the column is restricted. Using the symbol for a fixed support, we can model this example like so, where the vertical line represents the column. If a horizontal force were applied to the top of the open-ended column, it would deform like so, with the fixed end not rotating or being displaced. A real-life example of a pin or hinge support is this column connected to the foundations, as at the supported end of the column, displacement is restricted, but the column can rotate. Using the symbol for a pin or hinge support, we can model this example like so, where again the vertical line represents the column. This time, if a horizontal force were applied to the top of the open-ended column, the column would not deform, as the support allows for the rotation of the column. Finally, a real-life example of a roller support is this bridge connected to the foundations, as at the supported end of the bridge, displacement is allowed along the line of the roller's path. Note in this example, however, that the support restricts the bridge's rotation. Using the symbol for a roller support, we can model this example like so, where the horizontal line represents the bridge. Notice here the tip of the support is a point and not a circle. This represents the fact that the support does not allow for rotation. If the support did allow for rotation, it would be modelled like this. If a horizontal force were applied to the bridge would not deform, as the support allows the bridge to be displaced parallel to the force like this. To recap what we have learnt then, we have introduced the different types of load distributions found in structural analysis, and we have introduced the different types of supports and how we can simply model real-life connections. In the next video, we will be learning how to calculate reaction forces at supports, working through some example problems to reinforce our understanding. So if you haven't already, make sure you've subscribed so you know when that video is released. This has been a video by Learn Civil Engineering. If you have found this video useful at all, please leave a like and subscribe to the channel to show your support. If you do have any remaining questions or would like me to cover a specific topic, please leave them in the comment section below and I will try to respond as soon as possible. Thank you for watching.